Good morning, good afternoon, everyone. I am pleased to have with us Dr. Soroush Mahjoubi, who is a postdoc at MIT. He is going to talk about data-driven material screening of secondary and natural cementitious precursors. Dr. Mahjoubi, as I mentioned, is a postdoctoral associate at MIT, and he's affiliated with the Olivetti Group in the Department of Material Science and Engineering, and also the CS Hub in the Department of Civil and Environmental Engineering. He holds a PhD in civil engineering from Stevens Institute of Technology. His research focuses on developing AI workflows for low carbon concrete systems, including material property predictions, carbon aware procurement, life cycle assessment, life cycle cost analysis, and automated low carbon concrete mix design. Thank you very much, Dr. Mahjoubi, for doing this, and it's all yours.
Thank you so much for the great introduction, Pranoy. Today's discussion is about the paper that we published recently on Nature Materials Communications on data-driven material screening of secondary and natural cementitious precursors. Let me start with the big picture here. As you may know, concrete is responsible for over 6% of the global CO2 emissions, and most of these 6% comes from cement clinker production, which is extremely energy intensive, coming from the process emissions and the heat generation emissions from the kilns. So we can see here that 89% of the cement carbon emissions comes from the clinker production. So the clinker is a bottleneck, and reducing it can be a pathway towards decarbonization. In a study that we have developed in MIT, we have found all the pathways toward decarbonization of cement-based products. We have identified 28 stages from quarrying all the way to the end of life, and we have categorized these strategies into two broad categories: material strategies like alternative binders, alternative cementitious materials to be exact, the one standalone binders that can fully replace cement and clinker, and one of the example of that would be the sublime system cement, for example. And then there are other strategies such as supplementary cementitious materials, the materials that can replace cement up to a percentage, but the cement and clinker would be existing into the mix. And there are some impactful pathways such as carbon capture that leads to 50 to 70% reduction based on our investigation, and alternative cementitious materials that can reduce the carbon emissions up to 90%. And but many of those strategies are not deployable yet at industrial scale. And as you may know, there are many projects right now. There are many big construction that are happening, especially for data centers, warehouses, industrial facilities, and we need to scale up. Sorry, you can hear noises from somewhere. Yeah, I was saying that we would like to investigate the additionality of these strategies, and also we would like to scale up as soon as possible so that we can deploy low carbon concrete at a scale now. So naturally, we look at supplementary cementitious materials, SCMs. These are already used and can reduce the emissions by about like 50%, for example, for granulated blast furnace slag. And but there is a major supply limitation for these for traditional STMs, such as virgin coal fly ash and blast furnace slag. They are geographically limited and tied to industries that are declining. So even though they work, they cannot scale to meet the future demand. As you can see in the left-hand side, we can see the ratio between the traditional alternative generation to cement productions, the summation of coal fly ash, virgin coal fly ash and slag, blast furnace slag, to the cement production in the United States. And we can see that this is a global, sorry, and we can see that there is a 27% reduction from 2002 to 2022 here. And in the right-hand side, we can see the density function of embodied carbon due to domestic fly ash transportation. This is relevant to the construction projects that are far away from these coal plants, and this leads to embodied carbon. And we would like to also have SCMs all over the states. So we would like to basically increase the pool of supplementary cementitious materials and look into the chemistry of the cementitious materials in a systematic way. This is the first study that looked into the chemistry of all the materials that exist in the cement and concrete domain. And we came up with this end-to-end AI framework that it goes from literature mining to knowledge extraction to material discovery. And we can walk through this pipeline. As we can see here, the first component here is the data connection. We have over 5.7 million papers in our pipeline in the Olivetti group. And I should say that now this number is about 13 million papers, and these are only the peer-reviewed papers. We didn't add in the archive papers, for example. And what we did here is that we put all the sentences and the tables that exist in the literature about cement and concrete. We did some keyword searching in the first place, and we identified over 20 to 30,000 papers that are relevant to our case. Then we would like to extract the information from the paragraphs and the tables. So this is the data connection part. And the second part is the data extraction part, where we want to extract the information about the chemistry of the materials. There is a large language model that summarizes everything related to each materials that we have identified in the paper. So for each DOI, this large language model summarizes the information about that specific material. And then we have the table extractor here. So we wanted to look into the compositional landscape of material. So like we can see the chemical composition as a indicator here, and a descriptor that can be used for knowledge creation and knowledge innovation components. So the table extractor extracts the chemical composition from the tables, and then we have a material classifier. We identified 19 different predefined classes, such as slags, fly ashes, mine tailings, and then we paired the chemical compositions with the material classifier output and the summarizer. which has a material descriptor and a concise sentence that describes that specific material. Then we developed a machine learning model, a multi-headed neural network to be exact, to predict three reactivity metrics: heat release, calcium hydroxide consumption, and bound water. And I'll talk about these three metrics in the next slides. And in the next step, we use this model to screen all the natural materials in the United States and beyond. So we linked another data set, I think it named GeoChem, and used the chemical composition as an input, and we wanted to predict the reactivity metrics of these materials so that we can locate new SCMs in the United States. We also, in parallel, investigated the reactivity profile of the byproducts and waste materials as well. So here is one of the example of the communicative LLM agents that we have developed. We used open access large language models, Mistral 7 billion pre-trained to be exact, and then two ChatGPT, I think 3.5 that we have fine-tuned for this exact task. And we have also evaluated the goodness of like the output quality for these agents as well, that I will show later on. So we can see that, for example, in this paper, we have an XML paper with relevant information. So with the use of retrieval augmented generation, to be exact, we have found this table to be relevant to our task. And then the LLM extractor put this information into a structured format that we want. And then a summarizer, as you can see here, inputs all the information about this exact material. For example, this is Kutahya type F. It's not known that this material exists. Like this material is a fly ash, for example, based on the table only. But we have retrieved information about Kutahya type F using a keyword searching as well as retrieval augmented generation with an embedding space within an embedding space to find out the sentences and paragraphs that are relevant for that describe the Kutahya type F, for example. And then a summarizer gives us a sentence or two that describe that material. And then this will be fed to the LLM classifier, and this classifier categorizes this material into different categories and subcategories. So in this specific study, we analyzed 88,000 research papers that were relevant for our case, 100,000 tables from the papers, and about 3 million sentences extracted from the papers. And we did a investigation on how many hours a human need to extract this information manually, and we found that it takes over 2 years to do this task. This is one of the examples of quality assessment. This is a retrieval, embedding-based retrieval quality assessment to be exact. We quantified the incremental value added by each correctly identified relevant table. And we used a large language model like the ChatGPT, I think 4.5, to as a judge here. So a small pre-trained and fine-tuned large language model is used here a pre-trained 4.5 ChatGPT was used here to decide whether this exact table is relevant to our case or not. And then we benchmarked that and extracted, did the benchmarking and quality assessment on the retrieval of the tables uh, uh, that came from different embedding models. So the the first two embedding models, MPNet and MiniLM, are two sentence transformers models, and BERT is a model that was trained based on the material science domain, and we use the embedding space of that for this retrieval as well. And there are many metrics that we have considered here, but I want to focus on two most important one here, the cumulative gain and the normalized discounted cumulative gain. So the cumulative gain is the one that quantifies the incremental value added by each correctly identified relevant tables. And we can see that, like, for example, for the cutoff 10 means that the first 10 tables that were relevant to our prompt, all of those were relevant for our case. And for 1000 cutoff, 940 were relevant for our case. I'm talking about the ALL MPNet. And for MiniLM, for example, this number is 993. It means that out of the first 1,993 tables were relevant. So based on this information, we decided to use the MiniLM. And in the next step, we wanted to see how many of the tables are relevant and how many of them are not relevant. So we can see the top K value here. So top K value represents the number of tables that we have retrieved. And the cumulative gain is the metric that I have discussed early on. And we can, with this investigation and sensitivity analysis, basically, on the top K value, we have found the number of tables that are relevant. And we don't need to go through all the 100,000 tables that we have in our data set. We only need to go for about 20 to 30. As we can see here, like the ones that we have selected was MiniLM, and in 20 to 30, we can capture most of those tables. So we don't need to go through the 100,000 tables and save some computational time and cost. This is a generation part of this pipeline where the model already retrieved the tables, the embedding model already retrieved the tables already, and now another agent will receive that table and wants to put them into a structured format. So we also did them. We have also extracted the information from about 30 to 40 tables, if I'm not wrong, and we use that as a benchmark and evaluating the quality of generation. So these numbers are against the human evaluation, basically. So there are three different types of LLMs that we have considered. The fine-tuned one, it's basically uh, a standard way of fine-tuning. 8-bit quantized fine-tune version, which is useful to fine-tune the open access models in your own GPUs. And it's faster, but compared to fully fine-tuning, is that the quality of fine-tuning is lower, basically. And then pre-trained ones, the ones that already pre-trained, like the ChatGPT API, and agent-based fine-tuning. In that case, we have like two agents working with each other in sequence, and we evaluated three levels in three levels. The relevance, whether the table is relevant, materials, whether the agent were able to detect the materials, the compositions tuples, the extraction of numerical chemical compositions. And we can see the results for ChatGPT 4, 3.5, and for these two types of LLMs, we used the ChatGPT API. And we can see that, for example, ChatGPT 4 has 1.5 trillion parameters. This is an estimation, of course. And then ChatGPT 3.5 has 175 billion parameters. And then the other model that we have considered is the Mistral 7 billion. This is much lower, a smaller large language model that is open access. And then two different types of agent-based fine-tuned versions. So for the relevance, we can see that the Mistral is performing very well when it's fine-tuned. But it's good for training sets. It's the ChatGPT 3.5 is even better for the training set. And then for materials, ChatGPT 3.5, we're able to have the F1 score of 1. It means that it never failed in the train set, but in the test set, again, Mistral fine-tune and ChatGPT have comparable performance. Then in the composition tuples level, which is a most important part of this and more, let's say, complex. ChatGPT performs better compared to other models. And of course, ChatGPT is cheap, the end-to-end time for ChatGPT is lower compared to the open access model that we have used. So this is a part that we have investigated to make sure that the quality of generation is good enough. Now I want to show you how the extracted material descriptors are generated and why they are important. So we can see that again, the same exact example, the XML table we can see here that goes through the Mistral 7 billion, and then the embedding space retrieval, and then at the end we have the material descriptors. And many times material name is something not representative at all. For example, L here represents limestone filler. But if we only check the tables, we cannot notice that. And something like S, which means like in this exact DOI, it means it's a blast furnace slag, but the abbreviation is S, and we cannot figure it out what type of material is that. So this kind of material descriptor helps us to classify those materials, and also there are some important information in the descriptor that can be used um, for further literature mining. Um, Here, we would like to see the material classification and how it works. We have made 300 descriptors manually, and then we categorize them manually, and then checked against the fine-tuned ChatGPT 3.5. And we can see that the multi-class accuracy for categorization only is 97%. So one of the things that are important, and we are now using like there is another like application for this chemical composition data set that we have developed, is that we can now find out all the type F fly ash, for example, from all these data points, and it is much easier this way. For example, if you type F and fly ash, you can easily retrieve this data set. And one of the reasons that we used categories and subcategories was that. Here are the results of the chemical composition extraction. We have identified and extracted 17,000 materials from 6,000 journal papers. And I should say that this is also ongoing. We are adding more papers, and we are also adding in a vision-based large language model, VLMs, to extract the information from the figures as well. And that would be a complementary pipeline for this existing pipeline. And then we can see the variations of chemical compositions here in the left-hand side. There are some significant variations in many of those predefined categories, such as biomass ashes, and for example, let's say like construction and demolition waste, for example. And this makes sense because biomass ashes come from different feedstocks and biomasses, for example. And then we want to also show show these data points in the ternary diagram of the three major oxides, SiO2, CaO, and Al2O3, that have an impact on the reactivity and the chemistry of cement and concrete. And so this is the biggest data set that ever built for cement and concrete systems. We can see some clusters of materials in this space. For example, for slags, we can see that most of them are in here in this space, between 40 to 60%, for example, the CaO. And then for silica fumes, most of them are in this part, like very near to 100% SiO2. And these numbers also have some meanings. the first number here, for example, for silica fume, is the number of different materials that we have extracted, and the second number represents the number of papers that we extracted the information from. And for example, the cements, we have extracted 3,436 different types of cements from the literature. And there are some new clusters that are happening. For example, here, the high alumina cements and clinkers, which would be the aluminum silicates cement, and which is very interesting. In the next phase, we used the R3 test and modified R3 tests to basically link the chemical composition with the reactivity of these kinds of materials. We used three metrics here: heat release, that shows how much heat a material gives off when reacting in a simple lab mix. Then the CH consumption, how much calcium hydroxide it consumes, which signals the pozzolanic behavior, and then the bound water, the water that is tied into the reaction products. And we used bound water as a triangularity for the degree of reactions or reactivity. So that both bound water and heat release represents the degree of reactivity, while CH consumption represents the pozzolanicity. And the higher number for heat release represents generally mean a more reactive precursor. And we can see the classification of different types of material based on the existing studies in this domain. Some of those papers were published by Pranoy, and we can basically categorize the materials based on these two metrics: heat release and CH consumption. So now let's see what goes into the second model, which is the reactivity model. We have manually extracted 1,800 data points from 30 publications for chemical reactivity predictions of materials. These are the input variables: chemical compositions, a specific gravity, mean particle size or D50, and amorphous to crystalline content. This is also very important and represents one of the physical properties that impacts the reactivity. And Professor Olivetti here at MIT did a lot of job on the amorphous to crystalline content and dissolution in general. And we have also considered that in this study. And the output variables are the heat release, CH consumption, and bound water. I would also say that we have also parameterized the types of the testing as well, so that we can improve the generalizability of the model. Like the duration of the test was also an input. And with that, we were able to use not only the R3, but also the modified R3 tests results. This slide shows the accuracy of the reactivity model in practice. So the multi-headed neural network that we used can accurately predict the three metrics that we have considered. And we can see that the correlation of determination for all of those are over 85%. And one of the most important metric that we considered here is the heat release, and for that, the R square for the test set is 90.93. So based on the results, we can say that these kinds of models can be a fast way to shortlist the candidates for further for shortlisting the candidates to do the lab validation. And with that, we can have targeted lab tests instead of doing Edisonian approach of trial and error. Okay, here, so we applied a types of explainable AI model to open the black box of the neural network, for example, to be exact, sorry. And these kinds of methods can be used to rank the most important features that were considered as an input. As well as that, we can explain how the model predicts based on these features that we have considered. This is the results. In the right-hand side, we can see the feature importance and the SHAP value. So SHAP is a model agnostic method that relates the direction of the feature and the magnitude of the feature on the outputs. So for example, we can see that by increasing the age, for example, the age means the duration of the test, the heat release increases. And for example, another factor here is the CAO, for example. By increasing the CAO, the heat release generally increases and things like that. And based on that, there are many other things that we should mention here, like the amorphous content. With higher amorphous content, this leads to higher heat release, and this is rooted in the chemistry of these kinds of material. More Al2O3 leads to more aldehydrates as well. CaCO3, which is addition to the mix, can boost the carbon aluminates, and for example, high CaO in other investigation that shows that can shift the behavior away from pozzolanic calcium hydroxide consumption, and we can see that the model logic generally aligns with the domain knowledge in the concrete space. We have also looked into the subcategories and subtypes of materials, and we wanted to see and visualize the reactivity landscapes of materials. So in the right-hand side, for example, we can see the reactivity landscape for the defined materials that we have considered, and we can see that like metakaolin is the one that has the highest heat release and highest CH consumption, and slags, we can see that it has more hydraulic behavior, and silica fume, for example, has one of the highest pozzolanic behavior. And in the left-hand side, we can see like a slag subtype is also very important. For example, the copper slag has one of the lowest heat release, while the blast furnace and steelmaking slags may have a high heat release and high degree of reactivity. I should have a I should also note that we have assumed the particle the physical properties here in this study. Like we consider that the particle size is equal to a number, and we consider the particle size to be exactly the same for all of those materials. So these kinds of investigation can signal the need for signal the potential that exists for these kinds of byproducts. And in the next step for this study, we are currently working with our partners in the industry to test those materials that have a high degree of reactivity, basically. So these are the results from the 1 million samples representing 16,000 distinct rock types around the world, and we have evaluated the reactivity profile of these types of rocks. Again, we have assumed the physical properties here because we only have the chemical compositions, and we have imputed the amorphous to crystalline content. So far, we have identified 20 rock types here as potentially reactive, and for example, we can see that there are 5% of their samples exhibiting high reactivity, and we were able to find I think 12 of these rock types that have been found earlier as a SCM. Like something like pumice, silicic tar, for example, ignimbrite, rhyolite, anorthosite, all of those types of rocks have been used as SCM early on. Okay, here we can see the geospatial and reactivity profiling of natural cementitious materials in the United States. We have identified candidates in the east as well as the west, and we can see that there are over 6,000 natural samples that have either moderate or high reactivity profile, and most of them are volcanic and I think about 20% of them are sedimentary rocks. In this figure, we can see the number of reactive to total ratio, and if it's higher, it means that the number of samples that are reactive are higher and can be a better candidate. And the other is the number of samples that represents the abundance of these kinds of rocks. And with that, we have shortlisted the rocks that we want to investigate in the next step. We also saw some clusters that are happening in familiar geologies. like Appalachians, Rockies, Yellowstone, Rift Zones, and the Canadian Shield over here. We can see that there are some clusters that are happening, and we can um, basically increase the supply of SCMs where the traditional SCMs doesn't exist in that region with natural materials. One of the things that I have to mention is that we have also worked with companies around the world in Europe, in South America, and so far we have evaluated a couple of samples in Brazil, and the good news is that they have found new sources of SCMs there. And basically the results match the ones that they have identified. They have identified earlier, and then the new potential SCMs that we have found, they did an investigation and found that they have the potential to be used as SCMs. Here are the key takeaways here. We have identified the unique materials with distinct chemical signatures from diverse sources. Sorry about this. I think it's 17,000 in the second version. And then we have used LLM pipeline to classify those based on the material types and descriptors. We mined the chemical compositions from the literature with pre-trained and fine-tuned large language models, and we used a neural network to predict the reactivity metrics based on a separate data set of 1,800 data points. And then at the end, we mapped and ranked the natural precursors around the world and United States. That was all.